Today's webinar will be about advanced computer vision techniques and their applications to grape breeding. My name is Janet Van Zorn, and I'm part of the Extension and Outreach team for VitisGen 2, as well as an Extension Support Specialist for the New York Statewide Viticulture Extension Program. Before we begin the presentation, if you move your mouse to the bottom of the screen, you'll see a few icons. You can click on Chat to open the chat bar and use it to introduce yourself, make comments, or to alert me if you're having technical difficulties. Just please change the chat settings to Send to all panelists and attendees so everyone can see your introduction. Another icon on the bottom menu is the Q&A button. You can use this space to ask questions. We'll have time for questions at the end of the presentation, but you can type them in at any time during the talk. Our speaker today is Dani Martinez. Dani is currently a postdoc at Cornell University in David Godori's lab. He uses his background as a computer science engineer with a specialty in robotics to help advance phenotyping and automated systems with the VitisGen 2 project. And with that, I'm going to pass the screen and the mic over to Dani.
Hello, can you hear me?
Yes, perfectly.
Okay, that's nice. I'll try to share my presentation. Let's see. Okay. So can you see it? Okay.
Yep, looks great.
So let's get started. Thanks for the introduction, Janet. Hi, everybody, and welcome to this webinar. It's quite possible this is going to be a little bit different than the other webinars or seminars you usually have in your departments, basically because I cannot teach you anything about biology or similar things, because my main expertise field, as Janet said, is computer science, engineering, and robotics. So in this webinar, I'm not explaining anything practical for specific solutions for specific problems, because there is no way to do so. Every problem has its very different ways to be addressed. Instead of that, I'm only going to show you what is computer vision, its basic concepts and methods, newer approaches, some tips if you have to deal with it in your projects, and also a detailed review of the work we have done during the last year as a case of study for the VitisGen 2 project. So this is, one sec. Oops. Okay. This is the index. I'm going to try to explain you the whole world of computer vision in this presentation in an easy way to understand to people that is not very familiarized with this science. But my only objective is only to change your opinion about computer vision from it's basically magic to it's something hard and tricky. I would be happy if I achieve that. So let's start for the context and background. Okay, digital imaging. This concept is probably familiar to you, but I would say that most of you don't know what's behind it. I'm going to start describing different image sensors for digital imaging you may have already used. First, most common used one, the RGB light intensity based sensors. We can find this kind of sensors in conventional digital cameras, your smartphones, and a lot of different places. They are based on an array of light sensors that detects specific light wavelengths that are categorized as red, green, and blue. This is RGB. With the combination of these three bands or colors, we can represent any human observable color in a digital way. Then the next ones are the hyperspectral cameras, multispectral, which basically is the same like the previous ones, but it skips the step of categorizing the light by colors. They store all the light intensities by different wavelength ranges, including the spectrums that we cannot see, IR or UV. By using these devices, obviously we have more accuracy, more detailed information than the RGB sensors, but they generate lots of data that are more tricky and slow to process. The last interesting sensors are time of flight based sensors. they basically emit invisible light, usually IR, and they compute time difference between emitting that light and when they return back to sensor. Then they can compute the distance from the sensor to an object. So it's similar on the technology used by radars. It's a different way of imaging, but also widely used in robotics, especially useful for gathering physical information. But in this webinar, I'm going to focus on the light intensity RGB sensors to make this easier. So I'm going to start explaining the virtual representation of our RGB or our grayscale image in a computer. You probably know that digital images are composed by pixels. So that's basically how the computer stores them, like a matrix, a data matrix, or an array, in which its position, its position is a pixel, and it contains a numerical value of the color of the light intensity. So basically, the size of the data matrix is the same than the size of the image itself in pixels. If you are dealing with color images, for example, that matrix will have 3 different layers, one per each band. If it's grayscale, we will only have 1. Remember the combination of these 3 layers, like we have here an example image with the 3 separated colors layers. If we stack those 3 colors, we obtain the resulting image. They can also, this kind of data matrices, they can also store, besides of colors or light, they can store thermal intensity, like temperature for thermal imaging, or depth values for time of flight sensors, or so on. But as I said, we are going to focus on conventional color imaging. There is an important concept in digital imaging and computer vision, the color spaces. Color spaces are like a map with coordinates that are used to find a specific color. For example, the most used one is the RGB, as you know, the red, green, blue. So for example, if we want to find the color brown, that color has a specific value of R, a specific value of G, and a specific value of B. It's like a coordinate wall. If you follow those coordinates, you will find that brown, for example. But also there are other color spaces like the luminance and blue-red chrominance, or IUV, and the HSB color space. Those, we are representing the same colors, but they have different coordinate systems to reference the same colors. Having those different color spaces is useful in computer vision because some of them can be more handy when we want the computer to classify specific colors that we are interested to find. For example, the value 100 of red in the RGB color space is like brighter than the value of 50 red, but for us it's still red. If we use, for example, the H component of the HSB color space, the value 30 of the H, it's the red, but it includes all the different brightness levels of red. So it's like a different way to reference colors. The next concept of digital imaging that I would like to show is the image processing. Image processing means any operation or algorithm that uses an image as input in order to generate useful data as output. To me, it's important to distinguish between 2 different kind of image processing: the offline processing and the real-time processing. The offline processing is when we don't really need to have immediate results in the next few seconds or less, so we can store those input images for later processing. This is the way to do when the processing requires intense computation. Otherwise, online processing means that you really need to have immediate results, because you have to use that data to decide at the next step. For example, you have a robot going straight towards a wall, but it has to stop because there's a wall and it's gonna crash. So the cameras has to identify that there is a wall on that, or sensors have to identify that, and they have to make the robot stop. So that's why it requires to be processed at the same moment. And this kind of processes must be fast and optimized. Next concept is the light invariance, or the illumination factor, which is the enemy number one of all computer vision methods. Maybe it's hard to understand for us because we have like a super trained vision system, but the computer does not have it. For example, this blue color in the background of the presentation, for us is more or less the same like this other one, a few inches on the left, but for the computer is different because there's a gradient, there are different brightness levels. But for us it's still the same color. So we have categorized that as blue color, but the computer doesn't know about that. You have to explicitly specify what color is, which values of ranges are that color. But think about that, if we are outdoors, there's sunset, nighttime, or sunny, different kind of conditions, we are seeing different colors for the same original colors. That may be so messy. But that's why our brain is so powerful, because we can identify a color in different conditions, but the computer cannot do that. That's why it's so challenging. So look at this picture, for example, this picture on the right, here. It's a book page with a variance on lighting. If we tell the computer to look for white pages, it will give us this other picture. It's basically for the computer, this white area is a page, and the rest of the black area is something else. But for us, we still identify the whole image as a page. So that's why it's challenging if we cannot control the lighting conditions. So some brief advices to deal with that: avoid to use hard-coded color values, try to use other color spaces that can be more useful, can work better, or I would recommend to set up our controlled environment with controlled lighting and everything controlled if it's possible. So the main objective of computer vision as a science is just to try to emulate or improve the human sense of sight and its related decision making, mainly because we want to automate some process. Here there are some of the current application fields that is currently applied in industry, robotics, autonomous vehicles, medicine, biology, lots of different areas, and probably it's going to be it's currently growing presence. Okay, now that we have a better understanding on the context of computer vision, let's see some of its most used and basic techniques. First, this is probably the most used resource in computer vision and in any kind of methodology from the most basic ones to the most complicated ones. Masking. A mask is an image of the same size as the image that we are going to process, but instead of storing color values, as we previously seen, it stores zeros and ones. It's a binary decision, false or true. Zero means that I'm not interested in what value is in that pixel, whatever it contains, and ones means I'm interested in what's in there. So the resulting pixels that contains ones conform what is called the region of interest. Usually, the ones are represented as white color and the black ones and the zeros as black. And this mask can be the result of any kind of computer vision process. For example, a process that detects the skin or detects leaf tissue. It will return this mask in which the ones are the leaf surface and the black, the zeros are the rest of the image. So we are not interested in what's that. So color segmentation is another basic technique. It's basically when we use logical, when we want to detect a specific color or specific color ranges. We use for that logical expression. For example, I want those pixels that have a grayscale value greater than 75, or another example, red value less than 150 and blue value bigger than 200. This is an example, but this can be somehow tricky. This is the most easiest way to address this kind of color classification. So it's important just to mention that usually in digital imaging, the color values are represented from 0 to 255, which is the range of that a byte can represent. So this methodology, every pixel in the image is evaluated with this logical statement. For example, if that pixel has a grayscale value bigger than 75, it will put 1 in the mask, in the resulting mask. If it doesn't fulfill with this logical expression, it will put 0. Other processes that can return a mask as result, for example, edge detection, sets ones at the pixels that consider as an edge because there is a high color contrast, fiber metric, another one that detects tabular structures in the images by some filters and sets them as ones, and there are a lot more. So sometimes, well, I would say always, masks are not usually perfect because you can have noise, background noise caused by illumination variance, or simply because our algorithm is not good enough. Fortunately, there are some methods that are applied to masks in order to minimize this issue. Those techniques are known as morphological filters. Here there are two of the most basic techniques, erode and delete. They are algorithms that they are mostly already implemented in all kind of computer vision frameworks, so you don't have to worry about implementing them. For example, the erode algorithm simply gets the mask and slims the blobs composed by ones, the region of interest. That's useful when we have isolated ones in the image caused by noise. So this technique would remove those isolated ones, would remove that noise. And on the other hand, the delete technique does the opposite thing. It makes the region of interest bigger. So that can help to remove the holes inside the region of interest because we want to have a uniform surface. So there are our popular morphological filters. This one is pretty popular in biology, the Watershed filter. Suppose we are trying to count cells or similar shaped objects. Sometimes they touch each other and there's no way for the computer to distinguish between one cell or one blob and the other one. Because you see the resulting mask of the segmentation process produced. It's for the computer, all it sees ones and zeros and it cannot distinguish between cells because they are all touching. So using this filter, this morphological filter, it's able to separate those blobs, circular shape or squared shape. blobs. It's pretty useful, I would say. But at that point, the computer is still seeing only ones and zeros. It cannot distinguish among one blob, one cell, or the other one. So it cannot count them yet. That's why it's used the connected component labeling method. It basically transforms a mask of zeros and ones, like this resulting image, to a mask that contains zeros as background, ones as object one, twos as object two, threes as object three, and so on. So now the computer can distinguish every single blob, which are separated objects. So at this point, now that we have located all the different objects, so the next and the final step is the feature extraction. There are a lot of already implemented methods to obtain this kind of information. For example, the area in pixels, its perimeter, its orientation, the eccentricity, which is like how circle shaped is the blob, the location inside the image, very important. We have to aim or something, and a lot more features we can extract individually. And okay, that was all that is considered like the basic computer vision methods. Now let's see a few of the advanced ones. First, previously we have seen the color segmentation that is based on specifying a range of color values that we are looking for. But that can be sometimes annoying when you are trying to find the right color, because you may be interested in finding different colors that are far away in the color space, and it's not very handy to cluster them. So there is a way to be extremely accurate on that. It is by using a lookup table. First, using this method, first you have to create the table. It's very easy, the table, but manually selecting the colors you are interested from sample images. Then all these selected colors are stored in a table like this, which has the same color space that we are using, in this case RGB. So once we have labeled all the colors we are interested to find, it's as easy as checking the further images. Is this pixel with this RGB value inside that table? If yes, put 1 in the mask. If no, put 0. So you can also create this 3D table in order to look for different objects at the same time, like in the picture with these Lego pieces. You can manually label each one, and then it will generate this cluster 3D table, and it becomes basically like a clustering problem for classification. Yeah, next one. Sometimes looking for a specific color doesn't work very well. Like if we have to find this specific t-shirt in an image, it's going to be pretty tricky, right? So how we can tell the computer to find this in an image with uncontrolled background? Before the magic of the convolutional neural networks, there were few methodologies to face this problem. The template matching was one. This methodology is based on creating a data set of templates, which are small images containing the object that we are looking for, and it searches for similarities along the whole image to process. That's done by grabbing the template, place it above the image to process, and compute the difference on color values. But it has to be processed in different positions inside the image. This green square that you see animated would be the template, which is sliding through across the image. That's commonly known as the sliding window. So the template is compared in this first position, all the position, then it's displayed with a specific offset and then compared again. The position with the last discrepancy computed value means that that's probably the location of the object you are looking for. Let's see an easy example of where is Waldo. We have this big, huge picture and the template with Waldo in there. This method basically would take this small template and will compare in each position in the big image, and at the end it will return the position with the less discrepancy, color discrepancy. Another popular advanced method is the face detection. This is gonna be brief, but I think it's interesting. This is one of the most used computer vision method. As the previous one, we can look for the color, mainly because there is a lot of many different skin colors. So we have to look for common features. Viola and Jones developed a very optimized algorithm for face detection 18 years ago, and it's currently being used. Probably I would say it's implemented in all your phones and all your digital cameras. It also uses a sliding window method, but instead of having specific templates, because we cannot do that, we cannot have templates for all the people in the wall. So it looks for patterns, common patterns like noses, eyes, mouth, and its relative position between them. And that's what is used for the location of the faces. Now let's see artificial intelligence. Here's the magical stuff. Sorry. Artificial intelligence is a very wide concept, and it's completely different than the concept of computer vision. We can use artificial intelligence for computer vision, or we cannot, or we are not, like all the techniques we have previously seen. So what's the difference between of that? In conventional computer vision techniques, you have to develop an algorithm to perform a specific action or to get the specific data from the image, like dealing with mask, filters, color ranges, and all that stuff that we have previously seen. And what means applying artificial intelligence methods on computer vision. So artificial intelligence methods are designed to maximize the effectiveness or accuracy between input data and output results. AI methods don't care about images, about lighting variances, filters, masks, color, whatever. They just want input data to compute a result. It's like more or less they try to emulate our reasoning, because how we know that we are seeing a chair, because we have previously seen lots of chairs, but we don't know why we know that. We don't know if we look for the color. We can look for colors because there's a lot of different chairs, but we still rapidly identify that as a chair. So the concept is similar. How they work? It will be like, okay, give me this image that data structure that contains values, color values, lighting values, but I don't really care about what's in that. But I will multiply those values by these numbers I just made up, and then I will do the same, and let's see what's the result. The result can be yes or not, or a probability. And at that point, okay, my human master says that it's not correct, based on the training step. So let's do the same, but this time I will change those made up values for another ones, and let's see if my master like it more. So this is the procedure, but done like millions of times. At the end, you will have some values that magically provide the results you like. This entire process is called machine learning, which mostly uses artificial neural networks, in which neuron contains that made-up values that is being adapted until it works nice for you. Those AI methods usually require more computational power than the conventional computer vision ones, but they are a lot more robust, flexible, and effective. But we have to deal with images which are two-dimensional or three-dimensional data. The convolutional neural networks are the neural networks that fits better with this kind of data types. They have demonstrated very high effectiveness detecting complex features in uncontrolled environments. Just sounds magic. But look at this animated picture. It works like a sliding window we have previously seen. It takes a small piece of the image, it performs a convolution, which is a bunch of multiplications, and it gives the result to another smaller images. And it repeats the process until only one single value is obtained, which can be 0 or 1 or a probability between them. For the implementation of convolutional neural network, we have to specify its structure, so how many layers, neutrons, steps, so on. Create a training set, specific training options, and the further classification in order to use them. It's important to say that this is a pretty new research field, and actually there is no manual or theory about which kind of structure works better for any kind for a specific application. So it's all about experimenting and having experience so far. There is a new computer vision method that uses convolutional neural networks, which is called semantic segmentation. The idea is similar than the color segmentation that we have previously seen, but this time we are not looking for colors. We are looking directly for specific things or objects. There is no direct color association. That means, for example, that you can find the same exact RGB value pixel in a person shirt, like a blue shirt, and in a car painting that has the same exact RGB value. But using this method, that same RGB value is labeled as person in that place and as car in the other place. That means that this method is context aware. It's basically two convolutional neural networks, one followed by a reversed one. The first one classifies what's in every piece of the image, and when it knows it's a car, it's a person, it's a tree or whatever, it will expand that decision to determine which pixels can be considered as car, tree, or whatever. So it generates these labeled images. This was a summarized picture of all the world of computer vision. Let's have a brief view of application for biology. I will not go so deep in this point because I'm pretty sure you have a better picture than me about how you can use computer vision for your biologic-related projects. Instead, I prefer to explain you some key points about you should take into account if you are going to start dealing with computer vision. Computer vision in biology is mainly used to remove the common bottlenecks found data gathering from manual visual assessment. For example, by doing microscope work, feature categorization, field assessment, or any kind of phenotyping. Such conventional methods usually have important drawbacks, such as bias and ratings, requires a lot of time and energy, and human resources that make larger experiments completely unfeasible. So that's why it's proposed the concept of high throughput phenotyping, which is becoming more and more popular in biology thanks to the advances on the application of computer vision systems. This concept references the use of computer vision methodologies, but in a highly efficient way for automated visual feature assessment. It can also involve gathering other kind of sensory data beside images like temperature, humidity, lighting, or other readings. But it's important to say that beyond the scientific methodology proposals, the final implementations, all the final implementations will require people with engineering background in order to make the system robust, flexible, and portable. So come to show you some tips on how to create project on computer visions, or how it should be addressed, and other things to take into account very briefly. First step should be the identification of the requirements of the computer vision system we want to develop. This is the most important step, because if it's not currently done, we will waste time and resources in the following steps. Then start with development and validation. If at this point the validation shows nice results and they are acceptable for the final application, we can go to the next step, optimization and implementation. Let's have a closer look. Identification of the requirements. Most important thing is to define and specify the inputs and outputs of each computer vision process we want to develop. But it's also important to define them as specific as possible. I mean, in some projects, you might need several computer vision processes like targeting to something, background removal, detecting different things in the same image by using different methods. I would recommend not to create a single process that does all of it. It's better to have several independent processes, which is easier to debug and validate. And also, you can have time restrictions in a specific moment, and having all of them together would be a bad strategy, because we would require a lot of time. Also important, identify all the hardware you will need by each computer vision process. Make sure all the hardware is compatible with each other, because you would be surprised how often incompatibilities can show up. This can take a lot of time to make this study. The other important point, if possible, is the design of a controlled environment for the image acquisition to minimize the noise. If we are trying to use computer vision at outdoors, then things will be a little bit more complicated, a lot more complicated, sorry. But we still probably can find ways to reduce uncertainty. Important concept I would like you to remember: in any kind of computer vision process, the more stabilized and controlled is the environment, the less noise you will have in the final results. Examples: use a control lighting system that contrasts the features we are looking for, or brings a uniform lighting, use a uniform background, use a fixed camera stand, so on. Every detail counts. Development. Once the requirements and processes have been identified, now it's time to start developing them. Propose several methods that potentially can be effective detecting the feature you are looking for. Set up a comfortable workspace for each computer vision process and develop each process following their requirements and scores. When developing these processes, there are a lot of different software languages, libraries, toolboxes we can use. Choosing which one suits better for each process is important. I'm going to explain you something important to know about computer science, because probably I would say most of you don't know. This figure on the right is called the machine abstraction map. Any software or programming language has a level of abstraction from the machine to the user. We are here. That means that the more abstraction has that software, or the higher level is, the closer is to you, the users. That means that the easier to use for you, but it's less efficient. On the other hand, the less abstraction it has, or the lower level is, the closer is to the machine. Like the extreme case would be dealing with zeros and ones. However, it's possible to develop anything using zeros and ones, but that would be the most efficient way of coding, but impossible. For example, at the highest levels, we have software like ImageJ, you probably have used that, or MATLAB, even Python, and the lowest levels that we can use for computer vision is C, C++, and some OpenCV toolboxes. Why I'm telling this to you? Because if you have to develop a process with time restrictions, you will have to use a low-level language because they are much more faster than using MATLAB or Python. The same code programmed by using C can be more than 100 times faster than the same one programmed using MATLAB. If you don't have that time restriction and you need to use complicated algorithms, then you can use high-level languages, high-level software that they usually brings a lot of different tools for computer vision. But at the end, you can have different computer vision processes coded by using different abstraction levels. Oh my gosh, here. For important and ambitious projects, the validation step must be taken seriously, as well as spending resources on scheduling experiments based on preparing sets of input data and performing an statistical assessment on process effectiveness, comparing the results with manual ratings or other empirical validation methods. As almost everything in science, there is no method with 100% of accuracy. So it's the same for computer vision. At this point, you will have to consider to accept the current accuracy rate or going back to development in order to increase to try to increase the accuracy. This is like an exponential curve. There is a point where the relation between cost and accuracy gain becomes unfeasible. Optimization is always recommended, whether if throughput maximization is a goal or not. This is the same like the accuracy cost curve, but in this case will be the throughput cost curve. It depends on the resource we have. Once everything has been validated and optimized, then we can proceed to set up the final implementation, connecting the outputs to inputs, and perform a double check on all the whole system for unexpected behaviors. Now in this last section, I'm going to briefly explain you about the computer vision system we have been developing during this past year as a case of study. We are the phenotyping team of the VitisGen 2 project, which has been focused, we are currently focusing on development of high throughput phenotyping systems, in which the goal is the quantification and assessment of powdery mildew infection on grapevine leaf disk samples, which the final application of this methodology is the generation of high resolution mapping for natural resistance. At the beginning, two challenges or goals were identified. First one, to detect and identify colorless 6 micrometers wide fungal hyphus on the leaf surface. like in this picture on the right, these straight lines are the fungal hyphae on the leaf surface. And challenge 2 would be we were interested on more than 1,000 samples imaged per workday. So this is a list of the identified requirements for the development of our system. First, we needed to have a standardized and controlled container for the samples. Remember, the more control is of environment, the less noise we'll have at the end. So we decided just to purchase a specific model of glass trays and attach a grid sheet on it for sample placement. We need to capture as much as leaf disk area as possible, but also at the same time, we need to be able to see those fungal hyphae within the same image. So we decide to use a ultra high resolution camera with 4x magnification lens. In order to highlight those fungal hyphae in the image, we decided to build a custom angled LED system, which was especially designed for those hyphae. Then we needed to capture complete focus image because we are applying a 4x magnification, so we have less depth of field. That means that we need to capture several images in different focal planes. So we need to have some kind of robotic states that can move along the z-axis as well as the x and y axis for sample switching. The maximization of the samples processed per workday is important because we are dealing with biological samples which are time sensitive. They cannot stay eternally in that robot being imaged. So we have to speed it up as much as possible. So we had to spend resources on optimization, and of course, the final requirement was the detection of the powdery mildew, which we first proposed to detect white straight lines on the leaf surface, and other, we propose alternative methodologies. We'll explain that later. These two last points are not requirements, but are important things to take into account. There was no need to quantify powdery mildew at the moment that these biological samples were being imaged, as well as we don't need to stack the images when the system is working. So the intelligent way to design the complete pipeline was to split it into two different steps: image acquisition and image processing. For the development of the image acquisition step, we built this robotic system for the image acquisition, which is this one picture. This was the version 3 thing. Yeah, that means that we also develop a control software for the camera, for the robotic stage, for all the methodologies. And besides of this, for the image acquisition step, we developed 3 different computer vision processes. One for leaf disk aiming, in order to center the camera to a leaf disk. The leaf disk focusing, in order to place the camera in the correct Z plane. And the Z-stack image capture that estimates how many images the camera has to take per each sample. The more flat is the sample, the less Z-stack images we will need to have completely focused images. Also, we develop a graphical interface and all kind of stuff to make that easy to use for all the technicians and all other people non-computer science related. And Yeah, next, development of the image processing step. As the first solution, we proposed looking for straight tabular structures by using the fibermetric filter and the Hall transform that detects stripe lines. That was a good start, but was finally discarded because uh, it was very susceptible to noise from variations on the leaf surface texture, because we had a lot of different textures, hairy, uh, uh, well, probably know what kind of different leaf we can find. Then we propose to use, of course, convolutional neural networks in order to deal with these different contexts. So our current approach is based by using convolutional neural networks, but we divide each image by approximately 800 sub-images that are classified by using this neural network in order to detect whether there is powdery mildew or not. So the final result, the final score for each sample is the percentage of the infected sub-images that can be interpreted as percentage of infected leaf surface. You see these 4 images at the bottom are the same sample from the 2 days to 9 days after the inoculation day. We can perfectly see the infection growth. The convolutional neural network was first trained by manually classifying around 14,000 sub-images from 19 samples. This is wrong, it was 19 samples, I think. Then we performed a validation experiment where 3 experts classified the same 4,000 sub-images, as well as the convolutional neural network. First, validation results show around 90% of agreement between human experts and the convolutional neural network. So we consider that this agreed accuracy level regarding is pretty similar than the agreement among human experts. And just for finishing, we have currently 2 different systems that we are working on. First is the new version of the powdery mildew phenotyping robot, the Blackbird. You probably have heard about it. And the non-yet named robot arm for sample preparation. We are importantly increasing the throughput on sample imaging, but we are still preparing samples manually, and we have this bottleneck in the whole process. So that's why we decided to purchase a collaborative robot arm that will help us with it. And that was all. I think thanks for your attention, and thanks for all the phenotyping team involved in this development of this ambitious system. Can go with the questions, I think.
Okay, great. Thank you, Dani. That was really interesting and also really complicated. So while everybody's kind of like getting their minds around it, if you have any questions for Dani, then like I said at the beginning, there's at the bottom of your screen, there should be a bar with an icon that says Q&A. So you can just type in any questions that you have in that space and I can ask them. But in the meantime, I was wondering if you could talk a little bit about how widely applicable the program or the user interface that you developed might be, whether this is something that's sort of unique to the powdery mildew system, or it could be used for other diseases in grapes, or maybe even like completely different applications.
That's a nice question. So we first started addressing the powdery mildew problem by using this first version robot, but now we are developing the Blackbird, which is capable of imaging any kind of biological samples that has a maximum size of 1 centimeter wide. So we can place any kind of color sample like flowers, small fruits, whatever. This robot is able to image all these kind of samples, and then we can use those resulting images for finding any kind of feature we are interested on.
Okay. Great, it's really exciting. We have a question from Forrest. What kind of data processing capacity would be required in field? Could this be something that could be handled by drones, for instance, using a 5G network?
That's the thing. You cannot place a lot of computational power in drones. They only can be used for image acquisition.
Okay.
That's the limitation that they have. So you can, if you have to do online processing in the drones, that's not feasible. If they have to decide on a strategy based on what they are detecting at that moment, that's it's so far it's very complicated to do so. That's why now they are basically being used for image capturing, and then you have to figure out how that data that they capture is useful for you.
I see. Do you think that that's something that might be coming down the pipeline, or is that just sort of an obstacle that might never be overcome in terms of drones being able to assess in the field?
It will be in the future. I think that it will be solved, but so far the technology it's a pretty early. I mean, we just started using drones very few years ago. And everybody, I know that everybody is amazed about them because they fly and they're, but there's a lot of tricky things behind them, and also the battery depending thing, which is it's a very limiting factor.
Yeah. Okay, so maybe stay tuned in 5 or 10 years. Maybe that's something that could be
but
a little bit
the
more.
research on that should be done right now. But that research should be addressed by people that knows about that. This is specialized in that field, of course.
Yeah. We had another question from Michael who said, first he said, thank you for the talk. It was really interesting. And then also, could you discuss briefly the motivation for the project and explain a little bit more about sort of the reason for automating the detection of hyphae?
Oh, yes. Basically, the motivation was to maximize the throughput and have a really huge amount of data to create a very high resolution genetic map to locate the natural resistance of powdery mildew. So because every year we have lots of samples coming around the country, and that data has been used for the QTL association. Don't make me talk about that because I'm not so aware about that, but we currently found that there is higher level of association, the QTL analysis, than using the traditional methods that was just by manually counting the hyphae using microscope.
Yeah, if I can jump in here, this is Tim Martinson calling. So this offers people that are doing the grape breeding a big advantage over just doing field ratings. So field ratings are subject to all sorts of environmental variation, which can often sort of swamp out differences in disease resistance among the varieties. So this is a way of getting around that and getting a lot of detailed information about the different leaf samples and their susceptibility to powdery mildew.
Yes, this is our work only has been in laboratory level scale, not outdoors, because we are trying to control our environment as much as possible to have extremely accurate results. But if we had to do that out in the field, that would be completely unfeasible to detect that in early stages, for example, because you're detecting powdery mildew in very few days. Yeah, as I told you, it's a lot challenging any kind of imaging process in outdoors because of the environmental factors. It's not straightforward, and there is a lot of research on it. And if you get nice results you spend a lot of time developing an algorithm that brings nice results for you. If it's probably not gonna work so well if you use that in another place with other conditions that you are not aware. So it's pretty limited. I mean.
Yeah, the other advantage of this system is that it allows you to do take snapshots over time of the progress of the infection. So you might have something that, still allows infection, but the pathogen grows a lot slower or produces less spores or something, and that's what this imaging system allows you to do, because you can do repeated samples.
Yeah, our system is non-invasive, so we don't have to stain the samples or kill the sample itself. So this brings us a lot of flexibility to detect, even try to detect the spores, that fungal growth, or to extract a lot of statistical data from this kind of time growth.
Mm-hmm.
It's pretty helpful.
Bruce just added on to kind of this whole discussion with a comment. Basically, what Dani just said, that it's a non-destructive assay, so you can do a lot of computer imaging in real time over the course of time, and also that there's a limit of how long a technician can sit at a microscope, whereas the computer can, of course, not have to take breaks. So
yeah, we have estimated that in one day we can do the same amount of work that we were previously doing in 3 months.
Wow, that's really amazing. Another question from Anna Underhill is asking, with so many teams adopting computer vision techniques without having a unified platform for capturing those images, she's wondering whether that's leading to a siloed system without interoperability. So basically, without people being able to analyze each other's images, and how we can sort of work through that to come up with a system with better collaboration.
Like an open data set that people uploads all the images on, like, is open to.
Yeah, I think with the image capturing, and also maybe with how you're analyzing it, if everybody's kind of developing their own specific system, whether that's making it so that we can't really collaborate between teams, or is there a system in play to take care of that?
It can be perfectly done as long as the image acquisition system is perfectly the same. Because if there is any kind of minimal variation between the way the images were taken in a place and another place, then the methodologies cannot work like the same. If the image acquisition system is standardized, that methodology that Anne is suggesting can be pretty useful, I think.
Okay. Another question from Daniel is whether you can measure the rate of the hypha growth, the fungal hyphae growth.
Oh, we can, what was that?
Whether you can measure the rate, like how quickly it's growing, I guess.
The rate? The growing rate, you mean?
Yeah, like the rate of how quickly the fungus is growing.
Well, as you see in this forum, as in the example, you can you have the percentage of the infection by each day, so you can have a complete statistical vision. What's the growth rate of the infection by each sample? It's pretty straightforward in our methodology.
Okay, yeah. So the answer is definitely yes. And then a final question is whether you know of any other groups that are applying computer vision techniques to other aspects of phenotyping, or maybe even in winemaking or flavor or grape quality, anything like that. Somebody is interested in learning more or curious to read more, or even if you know of like a resource that somebody could go to aside from our website.
The wine, on the grape science, well, the grape field, you mean? I'm not sure about that. I probably yes, because lots of people is trying to perform this kind of automated phenotyping, but I'm not aware about anyone that has a powerful system just for address on grape vines or wine. I'm not so aware. I know that there's a lot of people working on different crops, on different plants, but I'm not so aware about the wine. Well,
okay. If anybody else has a response to that, if you want to type it into the chat. And I see that Anna Underhill just mentioned that a lot of people are using image analysis for cluster compactness.
Oh, yeah.
She was actually working on that in Minnesota. So.
Oh, yes, that's right.
Yeah. Yep. So I think that might be all the questions. If anybody has any last questions, then this is your chance. Type them in now. But otherwise, I think we've covered a lot of ground. So thank you, Dani.